So again, which of the following is not a method to terminate nanoparticles? Using surfactants, sintering, metal oxide support, applying electromagnetic field. Anyone? It's okay if your answer is wrong. There is nothing wrong in it. Okay, the answer to this question is sintering, because in case of sintering, you're basically applying more energy, and these nanoparticles, when you apply more energy, regulate these nanoparticles. I have only one or two questions left. Self-assembly of nano improves its stability. True or false?
True, sir.
That's correct.
True, sir.
That's correct. Focused ion beam technique has higher resolution than STM. True or false? Anyone? If you remember focused ion beam, what was it? We are blasting it with gallium atoms and we are etching the material. So will it have higher resolution with STM? STM, you could see atoms, you could move atoms.
It's true.
Now this is false. The answer is false, because in focused ion beam you cannot move atoms. You can only etch the atoms. You can etch the material. So you can't go below a few nanometer. In case of STM, you're moving atoms. So basically you're going into 0.25 nanometer regime. So therefore STM will always be the higher, it will always obtain a very high resolution compared to any other material. STM can be used to manipulate atoms. True or false? So the answer to this question is true. Okay, so with that, we come to the end of this first hour of lecture. What we have learned in this lecture, we have learned the importance of nanomaterials. We have seen how the nanomaterials are important in various fields. We have also seen that nanomaterials are all around us. Nature makes nanomaterials. Then we talked about the stability of nanomaterials, which is equally important as compared to synthesis of nanomaterials. And then we looked into the two approaches for developing nanomaterials. One is the bottom-up approach and one is the top-down approach. In case of bottom-up approach, in case of top-down approach, we discussed two things. We discussed about lithography, we discussed about ball mill, and then in case of lithography, we went down in discussing about how we can do nanomanipulation using lithography, which was based on AFM and STM techniques. So with that, I come to the conclusion of my first lecture. Is there any questions? I've not seen the chat, so I can sort of switch off this. Can I stop sharing, Rama?
Yes, sir. Yes, sir. Yeah, you can see in the chart box, I think.
Yeah. So, Bhaskar, and how can we maintain uniformity in ball milling? Yeah, that's a ball milling. Basically, unfortunately, you cannot maintain any uniformity. It is such a inhomogeneous process that one cannot really maintain this uniformity. So the only possible way is to go on ball milling for more and more time. Then you will get a uniformity. So you suppose you ball mill for about 24 to 30 hours, the possibility of uniformity is much higher. So that's the only way you can obtain uniformity. Okay.
There are questions raised by in the YouTube. So some two questions.
Okay, I have not got the YouTube link. I can only.
No. I'm just sharing you the questions.
Okay. Bhaskaran has again asked, how can we utilize bottom-up method for bulk batteries or other energy devices? Well, I will talk about bottom-up process tomorrow, not today. Today it's going to still be top-down process, and then at that time I can explain a bit more about the bottom-up process. What are Shrey Jain? What are your thoughts on exfoliation via sonication as far as viscosity is concerned? We will look into exfoliation in the next hour. So that's going to be completely on exfoliation and what are the parameters and to exfoliate. So these things will be discussed in the next hour. Okay, so I guess we have 50 minutes now, 51 minutes, yeah. So we can take a sort of 10 minutes break before we come back to the next lecture. Is it okay with everybody? Is it okay, Rama? 10 minutes break?
Yeah, it's probably. Shall we have 5 minutes, sir? Because
Yeah,
some participants may be left out.
yeah, okay, not a problem. Or
Maybe,
I
maybe.
can even continue. It's not a problem at all.
No, we will take some 5 minutes.
Yeah, okay.
Yeah.
So
Before that, I will ask the summary of the first hour lecture. So, for giving a summary, I would like to call Selva Kumar in the line. Hello, Selva Kumar.
Yes, sir. Yes, sir. Sir, is it audible?
Yes, sir. Fine, sir.
Yes, sir. Yes, sir. Very good morning. Very good evening to one and all. I am Selva Kumar, Head Department of the Chemistry, Mahendra Arts and Science College, Namakkal. It is my pleasure to conclude the second day first session of the virtual program, International Short-Term Course on 2D QDs, Synthesis and Applications in Electroluminescent Diode, Sensor and Solar Cell by Alagappa University and Brunel University. First of all, I extend our gratitude on behalf of the participant to our course coordinator, Dr. G. Ramalingam sir, and the university authorities to providing this online virtual course. Also, I'm happy to conclude this session. Okay, our resource person, Dr. Abhishek Lagri, Brunel University from UK. Sir explained our nanomaterial synthesis in well manner. He explained the importance of our nanomaterials, what are the approaches used for the nanomaterial synthesis, especially he explained that bottom up and top down approaches. Also, sir explained very well that a common method used in the top-down synthesis, that lithography, ball mills, as well as this is our new experience. Usually, our resource persons coming and give some notes and going. That is experience for us. Today, we faced faced a new experience. Our sir also asked some questions from our participants and explained that questions at the answering time itself. It's a new experience for us, sir. Thank you so much, sir. Thank you so much for your dedication for us. Really, it's a nice experience. Thank you, sir. Thank you.
thank you, Selva Kumar. Thank you very much.
Yeah, thank you, Selva Kumar, sir. Maybe another 5 minutes we will rejoin, sir.
Sure,
Yeah.
sure, sure, sir. Thanks.
Yeah. Thank you so much.
Hello.
Yes, Prakriti Kumar.
Yeah, sir. Actually, I didn't receive a link yesterday, and I don't also receive this schedule of the.
Okay, so no issue, because there is a technical problem between the YouTube and the live Google Meet. So no issue, you can continue this course.
Yeah, and I don't have the schedule. Means what is the schedule for this
Pardon?
short term course? Short term course schedule. I don't have schedule. Means at what time lecture will be there, and
I think you will get in the email.
no, I didn't receive, sir.
In the email you didn't receive.
No, sir.
Okay, so you will receive shortly.
Okay, thank you,
We'll check.
thank you,
Yeah.
sir. Thank you. Shall we start, Rama?
Yeah, yes sir, yes sir. Yeah, we'll continue.
Okay, let me first share the screen.
Yes sir, we are seeing the screen. Synthesis of nanomaterial, exfoliation.
So, can you see now?
Yeah, next slide.
Okay.
Yes, going on. Yes, yes sir.
Good. So, should I start, or we wait for a few minutes?
Yeah, I think the participants are not left out, so we'll start, sir.
Okay, good. So, welcome to the second lecture, which is on, we'll continue on synthesis of nanomaterials. And in this lecture, we will be looking at exfoliation. So, exfoliation to develop two-dimensional materials. So, the lecture will primarily be focused on exfoliation, the various techniques of exfoliation. Some of them will also include how the different variables for exfoliation, which I will talk through. So before we go into the lecture on exfoliation, so let's just have a small recap of what we learned in the last hour, We looked into the importance of nanomaterials and the stability of nanomaterials. We then talked about the different routes for synthesis of nanomaterials, which was top-down approach and bottom-up approach. In the top-down approach, we briefly looked into lithography. We looked into focused ion beam lithography. We also looked into the nanomanipulation using AFM, STM techniques. And we gave a brief introduction into bottom-up process. What are the different bottom-up approaches which are being used? So we will continue today in this lecture with another top-down approach, which is based on exfoliation. So what does the material in scales or layers? That's the meaning of exfoliation. It can although start with as simple as washing your face. So if it's a hot summer, you want to go home, wash your face. What happens during washing your face? With simple on your surface. So when you wash your face, this dead skin comes out during the washing. So therefore, that is also an exfoliation process. It can be considered as an exfoliation process. Why? Because you're removing dead skin, or you're removing your washing. Another example of exfoliation is when you see a very smooth rock surface. So if you have a hill which is basically weathered, and in weathering you have the wind which blows over the surface and removes layers from the rock, and this is why you have a smooth rock surface. What does it mean? It simply means an exfoliation. So what you have done is basically exfoliated the surface. Another example of exfoliation which is already there in nature, if you look at mica, if you go to beach in Kodaikanal, or if you go to any beach in even in Madras, you will see that you find mica on the beach sand. This mica is basically a layered structure of silica atoms. So therefore, mica is an exfoliated surface. So the water basically exfoliates the surfaces of mica, or it removes the silica from the surface in order to produce these kind of structure. So exfoliation, as we said, is basically to shed materials in scales or layers. What you're doing in exfoliation is applying a mechanical force. Ideally, you're applying a shear force of the material. So therefore, you're removing them in the terms of scales. So the question comes is, can we exfoliate any material? The answer to that is yes, you can exfoliate, but will it form a two-dimensional structure? That is a question which cannot be, which is not possible. So can we exfoliate any material? Yes, you can exfoliate any material, because what is happening in nature, we are exfoliating basically any material. So some of the materials which is of interest when we go into nano regime or nanomaterial synthesis is we want to exfoliate in the stacked layers of carbon atoms. And when you exfoliate graphite, you get graphene. There are other materials which are stacked together, such as black phosphorus, arsenic, antimony, bismuth nitride, nickel hydroxide, bismuth selenide or bismuth telluride, as well as gallium sulfide or germanium selenide. So these are some of the materials which have a stacked structure. And the stacking basically has van der Waals forces between the two different layers. So basically what you have to do is you have to get rid of these van der Waals forces in order to produce the two-dimensional structure. And more recently, the two-dimensional structure of MXene is of great interest to different applications. So a lot of research are being undergoing in developing two-dimensional MXenes. So how do we now exfoliate any material? Now there are three ways one can exfoliate materials. One is the mechanical exfoliation. You're simply applying a shear force. So you exfoliate the material. You have chemical exfoliation. Chemical exfoliation, although it is many journals, you will see that chemical exfoliation has been done, but it is not independent of a secondary process. So chemical exfoliation always includes either a mechanical or an electrochemical exfoliation step. So as such, there is possibly one or two examples only of absolute chemical exfoliation. And the third way is the electrochemical exfoliation. So we will, in this next hour or so, or next 40-45 minutes or so, we will look into all the three methods of exfoliation. So let's start with mechanical exfoliation. So in case of mechanical exfoliation, there are only two forces which can be applied for exfoliating. Because you have a layered structure like this, you can either take the structure away from the second structure, which is where you apply a normal force. The second is you're applying a shear force. So you have stacked layers, you apply a shear force, you're just moving one layer over the other. So there are only two ways one can use mechanical exfoliation technique to remove one layer from the other. So one is the normal force, the second is the shear force, or you can even combine the two forces. Ideally, when you do exfoliation of a particular material, you're basically combining both the forces of normal force and shear force. So what are the various ways one can do mechanical exfoliation? There are four ways one can exfoliate material using mechanical exfoliation. One of the way is sonication. The second is ball milling, which can be done as wet ball milling, or you can also do dry ball milling. You can use fluid dynamics method in order to exfoliate, and there are certain other methods which we will look through. So we will go through each method at a time. Let's start with sonication. So exfoliation with sonication. So in case of exfoliation with sonication, what happens during sonication is you're sending out waves at different frequency, and you're basically producing bubbles in the medium or in the solvent medium. When these bubbles basically burst, they are going to produce microjets. And these microjets are the main responsible particles, not particles, but solvents, which result in exfoliation. So when you have microjets, these microjets can act as a force which is normal to the surface. So you have a compressive stress force, such as shown in this figure, or it can have a shear force, which leads to a wedge effect. So these are the two ways a microjet can influence or break the layered structure. Again, to repeat that in the case of a layered structure, you have van der Waals forces, so you have to just overcome these van der Waals forces. Van der Waals forces are not very strong forces. They are not like hydrogen bond forces. The weak forces of van der Waals can be overcome simply by these microjets. So therefore, in case of sonication, the bubbles collapse to form microjets. These microjets then result in a normal force as well as a shear force, which leads to exfoliation of the material. So this is what the principle of exfoliation using sonication is. Of course, there will be many factors which should be considered during sonication. It depends on the solution. So it depends on the solution properties, the viscosity of the solution, the temperature of the solution. Definitely it will depend on these properties. The sonication frequency, it depends on what is the frequency of sonication, whether you are using, how many hertz are you giving for the sonication, how many bubbles are you creating. Is creation of lot more bubbles useful, or creation of small number of bubbles useful? So if you create a lot of bubbles, then basically you're going to fragment even the two-dimensional structure, which ideally you don't want. Or in some applications, you want them even more fragmented. So it depends on the sonication frequency. That also depends on sonication time. Temperature is an important aspect in creating these bubbles. Stability of exfoliated material. I always come back to stability because a lot of people don't think about stability. They always think in terms of developing nanoparticles and using them, but never think about the stability, because stability defines the properties of the nanoparticles and how long these properties are stable for a particular device. Now, another issue with sonication is you produce these materials, you have in a solution, whichever solution, whether it's water, whether it is a organic solvent or ionic liquid, you will have to separate these materials for a particular use. So you should know the separation, or how do you separate these materials. Simple filtration, centrifugation, these are some of the ways to separate. Ideally, centrifugation is a technique for separating materials from the solution. And finally, you want the material to be characterized so that to see that you have these functional properties. So these are some of the factors which one needs to consider when one does experiments with sonication or producing two-dimensional structure with So here is an example of exfoliation using sonication. So here we have a graphite flake, and this is the sonoelectrode. So when different frequencies are applied at the sonoelectrode, these electrodes basically produce a lot of bubbles, and you can see that once the bubble starts to collapse on the graphite flake, this graphite flake starts to expand, and as it starts to expand, it then exfoliates, it splits, and you have the shear force which forms over here, and it splits and exfoliates a lot of graphene. So this is an example of sonication to produce graphene from a graphite flake. I mentioned that temperature is an important factor. Now recently it has become extremely important, where they could see that temperature affects the properties of the two-dimensional structure. So a particular example was when they tried to develop two-dimensional quantum dots of molybdenum sulfate. So two-dimensional molybdenum sulfate quantum dots was prepared using cryosonication technique. So in this technique, they used liquid nitrogen in having molybdenum sulfate in it, and then they sonicated it to produce two-dimensional quantum dots of molybdenum sulfate. So temperature plays an important role, viscosity of the solvent plays a very important role in case of exfoliation, and at present there are no certain theories which can sort of say that this is the amount of, or we cannot develop a formula. It will be an empirical formula, it won't be a formula which can be derived theoretically from first principles. It will be an empirical formula to define what is the effect of temperature and various variables for sonication to produce these two-dimensional structures. So before we go forward, let's look at what really the video shows, or if we look at how the sonication technique is so we are basically sonicating a graphite substrate or graphite flake to produce graphene. So this is a movie which is done at 100,000 frames per second. Oops, sorry. I don't know why it didn't work. Yeah. So here you can see that you have started to produce bubbles, and still the graphite flake is as it is. Only when the bubbles interact with the graphite flake, you're going to have the exfoliation technique. So one can clearly see that only when you have bubbles which form microjets or collapses into microjet, then you're going to break this graphite into graphene, or you're going to form graphene from graphite. So before that, again, if we look at the video, just to make sure that everybody has observed it, we can see that you have already started to produce bubbles, even more bubbles, yet there is no exfoliation taking place. You have produced bubbles only when the bubbles come and interact. When you produce the microjets, it interacts with the graphite flake, and that's where you have exfoliation taking place. Before that, you do not have exfoliation. So the principle which we saw in two slides ago exactly is what is being observed experimentally. So this is the first way of exfoliating two-dimensional structure using sonication. The second technique which I would talk about is exfoliation using ball mill. Now we have talked about ball mill. There are different variables in ball mill speed, temperature, ratio between the ball and the material of interest. So there are various parameters which has to be adjusted for a particular application, for developing a particular two-dimensional structure. But the principle again remains the same. In case of two-dimensional structure or exfoliation into different fragments, there are only two ways. One, you apply normal force. What happens when you apply normal force? You're bending this material from the top, or you're bending the top layer and then overcoming the van der Waals forces. The second, you're applying a shear force which basically moves away these fragments. So this is the primary way in case of ball mill. This is the secondary way in case of ball mill. Of course, ball milling can be done either in wet medium or a dry medium. And when you want to exfoliate material, you can either use the wet ball milling technique or the dry ball milling technique. So an example, again, we go back to graphene nanosheets. When you have graphite flakes and then you ball mill it, you usually won't get very good graphene nanosheets. What was recently done was you add sodium sulfate during the ball milling process. So you add sodium sulfate onto the graphite flakes, and then if you ball mill and simply wash the material, so sodium sulfate will dissolve in water, so you can simply wash in water, you produce better graphene nanosheets. The reason for it is the sodium sulfate basically goes into or intercalates this graphite structure, and therefore it reduces the amount of force required to remove these graphene flakes. And simply by using or adding sodium sulfate, they could reduce the time of ball milling to obtain very good quality of graphene nanosheets. So this is an example of how ball milling can be used, or adding different solvents or and substances during ball milling to induce exfoliation of two-dimensional structures. The third way is the fluid dynamics method. Now, in case of fluid dynamics, again, I repeat that in case of a two-dimensional structure or exfoliation, we are applying a shear force. We only need to overcome the van der Waals forces. So obviously, fluid dynamics can be thought of a very beautiful technique. So in this case, in a fluid dynamics case, what one can do is put the bulk substance in an inclined plane, and then you flow the fluid over this inclined plane. So when you flow the fluid over the inclined plane, due to the viscous nature of the fluid, it will apply a shear force. Now, if you have done fluid mechanics, if you have studied fluid mechanics, you'll see that the Newton's law of viscosity, basically you're applying a shear force. So exactly you can actually calculate based on Newton's law of viscosity what should be the flow rate, what should be the fluid viscosity, as well as what should be the fluid temperature. So one can actually do theoretical calculation to overcome these, to break this two-dimensional structure by simply fluid flowing. So in this case, they did it in a slightly clever manner. If you now apply a centrifugal force of say omega, if you apply a centrifugal force, what you're doing is you can continuously go on exfoliating the bulk structure to a two-dimensional structure, and because of the centrifugal force, these structures or these can be separated out in one step from the bulk structure. And this is exactly what they did in 2014, which was published in Nature Materials. So I would suggest many who is interested in two-dimensional structure to go through this manuscript, because they explained very well from both theoretical point of view and experimental point of view how to overcome these van der Waals forces, and you can calculate basically how much force or energy is going to be required and what technique you need to follow in order to obtain two-dimensional structure. So what they did, instead of using this schematic diagram, they used a rotor in which they filled the graphite flakes. They filled the graphite flakes in a rotor and simply rotated it in a solvent. It was not water, it was different solvents. So they simply rotated, they took a rotor, they put graphite flakes into the rotor and rotated it in a solvent, and within fraction of seconds they could obtain large number of graphene materials. So you can see over here, these are bottles of graphene within 1 hour. So this was a unique technique and a very clear demonstration of obtaining two-dimensional structure from the bulk. Of course, this is not limited to graphite. You can also do with different materials such as molybdenum sulfate, cadmium sulfate, and things like that. Gallium selenide, things like that. So one can make this as a useful way. So based on this process, more recently, people simply used the grinder, which is used in everybody's household. So when they use the grinder, basically you are producing shear force, and because of the shear force, it will simply exfoliate and break into smaller structure. Now, the main disadvantage of any of these exfoliation technique is that you cannot define, or you cannot get the particular size. If, say, I want 1 centimeter square of graphene, it is not possible to get 1 centimeter square of graphene by using these kinds of exfoliation. The only way one can do of these kinds of thing is using the bottom-up approach, which is by chemical vapor deposition. So one of the drawbacks of top-down process or any exfoliation process is that you can basically get two-dimensional structure, but you have no control over the size of the material. So if I want a thin film, say if in case of industry, they want thin films of exfoliated surfaces. So although graphene was shown to have was discovered in 2004, for which they got the Nobel Prize, now it is 2021, and still you will see that very few places have use of graphene, real use of graphene. So therefore, you can see, although 15-16 years have passed, we have all developed a lot of structures, but still industrial application is very limited, only because there is no way we can control the size and shape of structure during the mechanical exfoliation. And second thing, in all the three cases, you see that we are using solvent. So obviously there are going to be always impurities in this graphene structure or any two-dimensional structure. So in case of using fluid mechanics, fluid dynamics method, this could be reduced. So in case of sonication, in case of ball milling, you'll always have more impurities compared to the fluid dynamics method. When we talk about other methods, this is the only other method where one can obtain two-dimensional structure. It is by using supercritical CO2. So supercritical CO2 is a different state of carbon dioxide. Because of high pressure and low temperature conditions, CO2 can be taken into a supercritical form. And in this form, what happens is carbon dioxide starts to sit in between the layered structure. And once it sits in between the layered structure, it is going to produce it is going to have a lot of stress within the structure. And once you depressurize it, or you bring the CO2 to atmospheric pressure, obviously CO2 is not going to be in its supercritical form. It is going to come out as gases. So once it comes out as gas, you will basically produce graphene structure or any two-dimensional structure. So this was one of the clever ways to produce relatively very pure graphene structure. So in this case, you can clearly see that we do not have to use any solvent. We do not need any other impurities present, CO2 will automatically be released when you depressurize, and you're going to get almost very pure graphene structure. So this is a very clean way to produce two-dimensional structure. Of course, you can look into this paper where they have talked about this technique, and there are certain number of papers which have come out after this of developing two-dimensional structure using this strategy. So these are the 4 techniques of exfoliation using mechanical exfoliation. So now let's look into what happens during chemical exfoliation. So as I said, there is no pure chemical exfoliation technique. There are very few exfoliation techniques purely based on chemical, because when you talk in terms of chemical exfoliation, you're talking about spontaneous exfoliation. So that is what basically you're talking about. So in case of chemical exfoliation, always a secondary process takes place. So for example, you have again a stacked surface. You introduce lithium ions into the surface or intercalate lithium ions. It can be lithium, it can be sodium, it can be potassium, basically any cation or anion which you can intercalate into the system. And then you apply a sonication, or you do ball milling, whatever. You can apply one of the mechanical forces, or you can even apply electrochemical technique, which we will see in the next couple of slides. And then when you have this, you're basically again producing a lot of stress inside the system. You're applying a small amount of energy, and then you have the two-dimensional structure. So you can obviously use different solvents if you want to functionalize this two-dimensional structure to produce desired properties of the material. So one of the only example which I could sort of find in chemical exfoliation, I'll show you in the next slide because it is in the video. So before that, I would like to say that there is one technique which is for chemical exfoliation, which is based on reducing graphene oxide. Although you can reduce graphene oxide, it's not a very useful technique for developing graphene, as the electrical conduct, if you're looking in terms of conductivity, your conductivity is always going to be pretty low for reduced graphene oxide. Now, the only example which I found for chemical exfoliation is the spontaneous chemical exfoliation of graphene, which took place in ionic liquids. So if you have imidazolium acetate as your ionic liquid, and you dip graphene into, or graphite flakes, sorry, not graphene, but graphite flakes into the imidazolium acetate in ionic liquid, then after some time, you will see that the surface gets exfoliated. So there is a spontaneous process which takes place during the reaction, wherein the graphite flakes gets exfoliated. This is because of the imidazolium cation which is present. So I'm talking about imidazolium acetate, which is an ionic liquid. The imidazolium cation, which is represented by this chemical structure, it is a pentagonal surface, pentagonal structure, which basically intercalates the graphite structure, creates stress, and automatically breaks the graphite structure into graphene. Obviously, the yield is very, very low. So you can see that it took 92 minutes for the surface to transform into a much more rough surface. The yield is very, very low compared to any other process. So let us look at a video which shows this is an in situ AFM which was done to see how the process takes place, or how the transformation between graphite to graphene takes place. So here what we see is a very clean surface of graphite flake. This flake is basically HOPG, which is highly oriented pyrolytic graphite. It is a very well structured process, and therefore you can see it in AFM that it is a pretty clean surface. So when I play the video, we can see that with time, the surface goes on changing. One of the things which you will observe during the process is that these lines get much more deeper, and after 150 minutes, you can clearly see that the surface is completely changed, and because of the chemical exfoliation in ionic liquid. So just to show the video again, sorry, we start with a clean surface. What you will see during the video is these lines become much more prominent. When it becomes much more prominent in case of AFM, what it means is these lines, you are basically removing the material and the depth of these things are improving. Therefore, you're producing graphene during the process. So let's see the video again. You can see the lines become much more prominent. That means you're removing quite a lot of material. And now you're going to start changing the morphology of the surface. It becomes a very, very rough surface after about 2 hours of the reaction. And after 3 hours of the reaction, you basically do not recognize the initial surface. So what you have done is basically chemical exfoliated the graphite surface, or the highly oriented pyrolytic graphite, which is known as HOPG. You have exfoliated that to form various graphene materials. So this slide basically, although it's a bit crowded, it shows the various advantages and disadvantages of different salts when you use for production of two-dimensional materials. I'm not 100% sure if everyone can see it, but basically when you use, so I'll just read out what it is. So when you use acids and bases, the main disadvantage is contamination due to oxidation and defects. When you use inorganic salts, again, it can lead to contamination. When you oxidize or reduce graphene oxide to graphene, or which you call as reduced graphene oxide, it has lower electrical conductivity. If you use etching agents, then especially this is applicable for MXenes, the material becomes relatively toxic. And obviously when you use functional materials, you're complicating or possibly depends on the application. If you want a particular application, then you're improving the applicability for that particular application. But if you don't want those impurities because of using certain solvents, then you're basically again producing impurities which will lead to undesirable properties of your material. So with that, we come to the final exfoliation process, which is based on electrochemical exfoliation. So we covered the mechanical exfoliation, we covered chemical exfoliation, we saw the various variables which one needs to alter in order to produce the desired two-dimensional structure which you want, as well as the desired properties which you want. Obviously, it depends completely on the application. Now we come to the final one, which is electrochemical exfoliation. And compared to chemical and mechanical, although you can produce a lot of material, the yield in electrochemical exfoliation is usually much higher because you have a lot of control over when you do the electrochemical exfoliation. So before I go into electrochemical exfoliation, a bit about electrochemistry. I'm not sure everybody is familiar with electrochemistry. Therefore, I made a slide to talk a bit about electrochemistry. So when it comes to electrochemistry, basically this is your setup. You can take up a beaker, you have 3 electrodes in it, and you have a tube which is over here. And you can either have a stirring bar or stirrer bar, or you don't have to have a stirrer bar. Now you have 3 electrodes in electrochemical system. You call this as working electrode, you have a reference electrode, and you have an auxiliary electrode which is also known as the counter electrode. You can purge various gases through the tube. It depends on what you want to do for that particular experiment. Now the the working electrode can be both either the anode and the cathode. It depends on what you want. So to change the 3 electrode system to a 2 electrode system, what you do is simply combine the reference electrode with your counter electrode, and that will define the potential. So in a nutshell, 3 electrodes is used for understanding the electrochemical reaction. 2 electrodes is good enough to do electrochemical electrochemical synthesis, such as electrochemical exfoliation. Now, in case of electrochemical exfoliation, in case of electrochemistry, based on the 3 electrodes, a lot of electrochemistry has been already understood, and this is the electrochemical series, which many of you will be aware of. Now, in case of electrochemical series, what you see is reduction potential. As you go down the series, the metal becomes more reactive, and as you go up the series, the material becomes more noble. So, for example, lithium is a very highly reactive metal, and it has a potential of 3 volts. Therefore, the battery which you have in your mobile phone maximum has 3 volts. Only you have to stack the batteries together in order to improve the voltage. You have to stack it in series to get 9 volts, 19 volts for the case of a laptop, and things like that. So lithium is a very reactive metal, therefore it sits at the bottom of the electrochemical series, and as we go up the series, the material becomes more noble. So copper is more noble than lithium, silver is more noble than copper, and therefore these are known as noble metals when you come to silver and gold and platinum. So they are so unreactive that they will have a positive potential versus the hydrogen electrode potential. So that's something to do with the electrochemistry. Now, in case of electrochemical exfoliation, why I talked about electrochemistry is, in case of electrochemical exfoliation, one can have the electrode as a cathode, or one can have the electrode as an anode. So when you have the electrode or the material such as graphite or whatever surface you want, if you have the electrode as a cathode, that means that you can, when you talk about cathode, you have a negative charge, so you will have positive ions which come into the material. And when you talk about anode is where an oxidation reaction takes place, and therefore you will have positive charge which you pass, and therefore you will going to intercalate the material with negative ions. So just to explain again, a cathode is a place where you have reduction reaction. So when you reduce a particular material at cathode, you oxidize particular material at anode. So when you have the graphite, we're taking graphite as an example. When you have graphite as the cathode, you can intercalate with positive ions such as lithium. When you have graphite as the anode, you're intercalating negative ions such as sulfate ions. So in both the cases, whether you take a graphite as anode or a cathode, in both the cases you will undergo exfoliation, but the mechanism of exfoliation is going to be different. That is something which you need to think about. So for example, you can take lithium sulfate as the electrolyte, take graphite as the cathode, and take something else as the anode. When you apply a potential between the 2 electrodes, lithium goes into intercalates, and obviously you're creating stress, and therefore it will expand and finally break down into the system. So this is the main principle of electrochemical exfoliation. So you can electrochemically exfoliate using 2 electrode surface. You can either take it as a cathode or an anode, but remember, when you take it as a cathode, you have reduction taking place, so you will have positive ions which will intercalate. In case of anodic exfoliation, you have oxidation process, so you're going to have negative ions which will intercalate. So it depends on what you want to do or what impurities you want in your material. So this is the basic setup of experimental setup for electrochemical exfoliation. You have your layered material, you make it as a cathode or an anode. In this case, we have the material as cathode. Lithium foil is the anode. What happens when you pass current through it, when you pass a potential through it, you have lithium ions which diffuse into the cathode, produce stress within this, and then that leads to exfoliation of this bulk material to 2-dimensional surface. So once it gets intercalated, it basically breaks down and separates out the 2-dimensional nanosheets. So that's the simple experimental setup for electrochemical exfoliation. So here is the image of how exfoliation takes place. Now you have the graphite over here in the solution containing lithium perchlorate in polycarbonate solvent, and you apply a potential of 5 volts between the 2 electrodes. So in the other case, the electrode is lithium. What happens during this case, you have lithium which goes into the polycarbonate, and if you add another cation into it, such as TBA, then you're going to co-intercalate both the cations during the process. And one can see from the optical image over here that you have expanded the graphite surface, and then here you have complete exfoliation or disintegration of your graphite to graphene. Now, in case of electrochemical exfoliation, why I talked about electrochemical series, one needs to understand a bit more. In case of electrochemical exfoliation, here we have something called SEI. SEI is the solid electrolyte interface. Okay, so SEI is a solid electrolyte interface, which is more relevant to people working in battery. They will understand SEI very clearly. So in this case, what happens is when you apply 5 volts, you are going to even decompose the solvent. And when you decompose the solvent, it is going to react with the lithium present in it. And therefore, this process of reaction between lithium and the decomposed solvent will lead to formation of SEI, and that can also, that basically will create impurities in your material. Now, why I talked about the electrochemical series before? The electrochemical series, I said that lithium has a potential of -3 volts. That means you have 3 volts, maximum of 3 volts you will get from a lithium surface, lithium metal. Now, there are no electrolytes which have a stability higher than 3 volts. It is thermodynamically not stable beyond 3 volts. Therefore, whenever you take whichever electrolyte, whether it is ionic liquid, whether it is organic solvents, you are always going to have a secondary process or a secondary reaction of decomposition of the product. And still a lot of research is going on to increase this cathodic potential of the ionic liquid in order for to develop high voltage batteries or higher batteries having a wide voltage. So therefore, in case of electrochemical exfoliation, when you apply 5 volts or some of them apply even 10 volts, you although have your exfoliation, but you're going to always have impurities along with it. Now, before I come to my last slide of the lecture, which goes into the latest topic of wireless electrochemistry. So we were looking into electrochemistry where we had 2 electrodes. One electrode was graphite, the other electrode was lithium, or whichever metal. You can take sodium as well, it's not a problem. You will have the same process. Now, this is a relatively new topic which has been looked into in the last 5-6 years, which is known as wireless electrochemistry or bipolar electrochemistry. So in this case, what happens is you have 2 electrodes. In the last case, we had one of the electrodes which was graphite, for example. In this case, none of the electrodes are graphite. You have 2 inert electrodes, and you have graphite powder, which is at the middle of these electrodes, which is not even connected to the 2 electrodes. Obviously, you're going to have an electrolyte, which is needed for electrochemistry. Now, a certain high voltage, so in the last case, we had 5 volts, but in this case, you pass about 50 to 100 volts. And what it does is you are going to have a voltage gradient between the 2 electrodes, which will trigger an electrochemical reaction in the graphite powder. And therefore, it will trigger, basically it triggers a stress within the graphite powder because you have applied a very high voltage between the 2 electrodes. And this is the reason why it is known as wireless electrochemistry or bipolar electrochemistry. So the material which is in the solution is not in contact with either of the electrodes, yet you're having an electrochemical reaction which is taking place. So therefore, it is a wireless sort of technology you can think of. And recently, using bipolar electrochemistry, one could produce relatively pure graphite powder, because in this case the electrolyte need not be a concentrated electrolyte, it can be very dilute electrolyte. Because of the voltage, you're producing the stress, and therefore the graphene is going to be relatively stable, relatively pure. There will be very few impurities in the graphite. Of course, there are lots of things which will depend on lots of parameters, which will depend for the wireless electrochemistry, which is given by this equation over here, which is the delta E electrode is equal to E total into I of the electrode. Of the second lecture, as we had in the first lecture, there's going to be a quiz based on all this topic. So the first question which I have is, can we exfoliate granite? Yes or no?
Yes, sir.
Yes, sir.
That's correct. You can exfoliate granite. And if somebody thinks that you cannot exfoliate granite, you can take a granite rock, hit it onto a wall, and you will see how it breaks. It breaks along a plane. It doesn't break into fragments. It breaks along a plane. Therefore, it is an exfoliation process. Sonication comes under which kind of exfoliation? Mechanical, chemical, or electrochemical?
Mechanical.
Mechanical, sir.
Mechanical.
That's correct, mechanical. In ball mill, exfoliation takes place only due to normal forces applied on the material. True or false?
False. False.
That's
False.
correct. It's false. Fourth question, does electrochemical exfoliation depend on electric potential we apply?
Yes, sir.
Yes, sir.
That's correct. That's correct. It depends on the electrochemical potential. So if we apply, for example, we saw 5 volts. If I apply 1 volt, will we have exfoliation? Yes or no? No, obviously no. You have to move the lithium ions. You have to move the lithium ions. It has to intercalate into the system. So you need more voltage. You require 3 volts for the lithium to go into the material. So you cannot use 1 volt when you're using lithium. So therefore, in case of electrochemical exfoliation, electrode potential, applying a particular electrode potential is a must, and it depends completely on electrode. One of the variables is electrode potential. Not all. One of the variables is electrode potential. My final question is, does electrochemical exfoliation follow the electrochemical series? Yes or no? Somebody said yes. Somebody says no.
Yeah, many of them are saying yes.
Okay, that's good. Yes,
Yes.
it's correct. It has to follow the electrochemical series because you have to intercalate something. You are having a reduction and oxidation process. So you have to do these processes. So it has to follow the electrochemical series. Good. So with that, we come to the end of this second lecture. What we learned in this lecture, we were looking into exfoliation of materials. We've seen that we can exfoliate various materials which are stacked together, and we looked into the different approaches for two-dimensional material synthesis, where we looked into mechanical, chemical, and electrochemical techniques for exfoliation. In mechanical, we looked into sonication, we looked into the technique of ball milling, we saw how fluid mechanics can be used. We also saw supercritical CO2, which can be used for mechanical exfoliation. Chemical exfoliation obviously was very limited, because only when you talk about chemical exfoliation, it is the spontaneous exfoliation you're talking about. In other way, you can reduce graphene oxide to reduced graphene, but you're going to have problems with the properties of the material. So very limited approach with chemical exfoliation. And electrochemical exfoliation, again, it became a relatively easy technique to exfoliate. Obviously, there were issues with regard to impurity. So although we talked about the three techniques, everywhere we had issues with impurities, and the second thing is we couldn't control the size and of the material. So these are the two aspects still of importance in terms of exfoliation of materials. Thank you very much.
Thank you, Professor, for giving your exfoliated the synthesis of chemical synthesis. So very detailed manner.
Thank you.
So yeah, this for concluding session, I ask the delegates Selva Kumar. Yeah, Selva Kumar, are you on online?
Sir, I am audible.
Yes, sir. Yes, sir. Please.
Sir, good evening to one and all. Again, this is Selva Kumar. Okay, on behalf of our participants, I am very much proud to give the conclusion for this session. First of all, I would like to thank our course coordinator, Dr. Ramalingam sir, and our resource person, Abhishek Lahari sir, from Brunel University, UK. Also, I would like to thank our university authorities for providing chance this courses in this pandemic situation. This session is much useful for us, sir. In this session, we this one, sir, discuss about the exploitation of chemical and mechanical exploitation methods, that techniques for development of nanomaterials, approaches used for 2D material synthesis, especially mechanical process, chemical process, electrochemical process. Today also we learned some new technique, that is wireless electrochemical process, that are much useful. We can utilize this knowledge in our future endowments. Thank you so much. Thank you so much for your presentation. Thank you, sir.
Thank you, Selva Kumar. Thank you very much.
Thank you, Selva Kumar, sir.
Thank you, sir.
Professor Abhishek, sir.
Yeah.
Yeah, thank you very much. And really, you are giving wonderful lectures. I think you are a good teachers in your university to explaining all the things in theoretical manner as well as in the way of practical approach. So really, in small video clips that help me to understand the process of exfoliation and all the synthesis process. So really it is helpful, and I hope that all the participants are enjoyed very well in this session.
I hope so too. They have not slept, I hope.
Yeah. So it's so great and nice to interact with you. And finally, there is questions with the audience, the feedback. So that will be very good actually.
Yes.
So
I've not seen. I'm just seeing the chat. I don't see any questions. I've only seen. I've not seen any questions. So if there are any questions,
there is one questions by Gopal Krishnan. So he asked the question that explain about the pristine 2D dots. I know about quantum dots as zero structure. Okay. And can you explain about the pristine 2D quantum dots?
I don't understand what you're talking about. I mean, what do you mean?
Yeah, maybe that Gopal Krishnan, maybe you can unmute and directly interact with us. So it is a common instruction for all the participants. So if you have any queries or suggestion, you please unmute and directly interact with us.
Sir, can you hear me, sir?
Yeah, I can hear you.
Gopal Krishnan, please introduce yourself and ask the question.
Sir, my name is Gopal Krishnan, sir. I'm a research scholar, sir.
Yeah.
From where?
From Chennai, the new college. University of Madras affiliated.
Okay, yeah.
Oh, sir, I need to know about the pristine I know the quantum dot is zero dimensional. Is it right, sir?
Yes, correct.
But the 2D quantum dots, what is the meaning of 2D quantum dots?
So basically what has happened is when you exfoliate, you're going to still produce few nanometer size. Okay, even if you exfoliate, you're going to produce maybe 50 nanometers, 100 nanometers. But when you talk in terms of quantum dots, you want it in 1 to 2 nanometers or less than 5 nanometer in size. Now, in case of 5 nanometers in one single layer of atom, how do you obtain that? Okay, so therefore they have looked into cryo sonication technique, because when you go down to a very low temperature, what you're doing is you're exfoliating, but the energy barrier is slightly lower. Because you've gone to such a low level, it breaks easily. So what happens when you take it into liquid nitrogen, you take a rubber tube in liquid nitrogen, it will break easily, right?
Right, sir.
Yeah, so your mechanic, it does not have any more mechanical strength. So
Yes,
now
sir.
if you take the two-dimensional structure such as molybdenum sulfate, which they have
Yes, sir.
explained, if you take graphite and put it into liquid nitrogen, it loses its mechanical strength. And now if you apply a very small amount of sonication, it will break into very small fragments. It won't give you large fragments. So if you take, for example, rubber tube in a liquid nitrogen, it will break into very small fragments. It doesn't break into the same phenomena they use for two-dimensional. So now you have two-dimensional structure which is of maybe 1 or 2 nanometers, and then you produce quantum dots.
Okay, sir. Understood.
Yeah.
Thank you, sir. Thank you, sir. Thank you, sir.
Hello. Can you hear me, sir?
Yeah, Jay, please.
Okay, so hello, sir. I am from Gujarat, and I am a research scholar from Gujarat University, and I am working on molybdenum disulfide 2D thin film. And I have a question as far as sonication, exfoliation via sonication process is considered. You said in a slide that the fluid jet that is produced, that should be, there are two possible. One is that the fluid jet is perpendicular to the flake, and the other possibility is that it is parallel to the flake, right? Ideally, what we want is that the jet should be parallel to the flake, so that sonication induced scission is not happening.
Correct.
Right? So is there any way to control this thing?
Unfortunately, the only way you can control, not in case of sonication, the only way you can control only the shear force is by fluid mechanics technique or using supercritical CO2 technique. In case of sonication, in case of ball mill, you have no way to control how the process is going to take place. So you have to go into the other techniques.
So even if we use a probe sonicator or a bath sonicator, it can't be controlled, right?
It is almost impossible. I mean, you can always try controlling it in a particular way, but almost impossible to only control based on the shear stress.
Okay, and another question is, a major component when considering sonication process is the surface tension of the material and the solvent, right?
Yeah.
They both should match.
Yeah.
So as far as the surface tension is considered, we can control the surface tension of any solution by changing the temperature or the concentration, right?
Yeah. Yeah.
So we can use any solvent for this process.
Yeah, basically any solvent. Yeah.
Okay, so we just have to, let's say we use water which has a surface tension around 75 or something like that.
Yeah.
At room temperature. So by changing the temperature and the concentration of the solvent, we can bring it down to the surface tension value of LHCMOS2, and then we can use it as a solvent.
Totally fine.
Okay. Thank you.
Yeah.
Yeah, then any other questions from the audience?
Sir, one last question.
Yeah, sure.
Okay, so finally, when we centrifuge the solution and obtain the nanoparticle solution, we can either drop cast it or spin coat it, right?
Yeah.
Get a film. So for drop casting method, like what are the most effective ways to overcome the coffee ring effect?
When you drop cast, again, you're using a particular once you centrifuge. When you're centrifuging, you can use different solvents. When you centrifuge, you want to centrifuge in water, you can do it in distilled water, but you can basically add various solvents. You don't have to use water for centrifugation. So you can add some amount of alcohol, for example, ethanol and things like that. Again, when you add alcohol, you have to make sure that your centrifuge is not plastic, because then again plastic will interact with the alcohol. So you have to make sure that which kind of centrifuge you're using. A glass centrifuge, glass tube as a centrifuge, that's perfect, because then you don't have the secondary reactions taking place. So once you have this, then you can basically, you're removing the surface charges, especially in alcohol, you're removing the surface charges, and then it becomes much easier for drop casting.
Okay, but like even if we drop cast that solution, it is very hard to overcome the coffee ring effect, where the solute particles arrange themselves on the border of the. So
yeah, because of course, when you have the surface charges, you have no way to control these things. One way to drop cast, if you drop cast with the electrode, so if you drop cast on a surface, for example, on a conducting surface, and you can apply an electric field on this conducting surface, then it can overcome these phenomena slightly.
Okay, so if we are talking about spin coating process, there has to be some viscosity of the solution.
Yeah.
Okay,
yeah.
So usually, let's suppose if I'm making my solution in IPA, so it has a very low viscosity. So the only solution I have is to drop cast it, because spin coating the IPA solution won't make much sense.
Work. That's correct. Yeah.
Okay.
Yeah.
Okay. Thank you.
Thank you, Jay. Yeah, so there is an important announcement that people, those who are interested for asking questions, please, you can unmute at the end of the session, every day. So you can unmute and directly interact with us. Okay. So, and before asking the questions, you please introduce yourself, because this is online, so we do not know where you are from. So please, you can introduce yourself very short, and then ask the questions. Yes, Professor. So this is a time for concluding the session. So we will conclude, sir.
Yep.
Yeah. So thank you so much for joining this today lectures. And today we have 2 lectures on basically of material synthesis. Tomorrow also we have another interesting material synthesis method by Professor Abhishek Shah. So tomorrow is going to talk on hydrothermal and servothermal methods, and then electrochemical and templated synthesis. So these are the other interesting areas of synthesizing of nanomaterial. So I request on behalf of Brunel and Alagappa University, so I request again to join all of you by this same 2 o'clock of India time and 9:30 of British time. So please join by tomorrow. The same the schedule will be sent to you in your email. So please check the schedule. And there is an important announcement that so you can unmute and interact with us at the end of the session. So that is allowed. Suppose if you cannot interact, then you can ask the questions in the chat box. So one thing. And the second thing, so there will be a there is a questions at the end of the session. So we have a planning to validate your presence during this course of work, in these courseworks. So there will be a set of questions will be shared at the end of this end of the day. That means the Friday. So you have to answer all the questions. So based on the question and answer, you will get the credit, and from the credit you will get the certificate. So minimum 80% we are expecting. So that is the second thing. And the third thing, the attendance. So attendance is must for maybe forget about the yesterday class. There will be some technical issue between the YouTube and the Gmail ID. So forget about yesterday, and from today onwards, the MHRD is seriously viewing about your attendance. So 80% of attendance should be there. So attendance link will be sent either by the beginning of the session or the end or middle, so whatever it may be. So do not ask any questions about just to share the attendance, just share the attendance. So no need to asking the questions in the chat box. So at the right time we will send the attendance. Okay, so you need to focus only on the classes, and at the right time we will send this attendance. And similarly for the feedback, so feedback form will be sent at the end of the course. That means the last day, the Friday we'll be sending the feedback course. So in the feedback course we'll asking all these details about the course and your valuable suggestion, etc. Okay, so this will be feedback course, feedback link will be shared only at the end of the session. Yeah. Okay, so any other matters, if you have any queries, you can just email us in the conference email ID, which we already know that, or sometimes you can share in the chat box. So with this, I think we will conclude this today's session, sir.
Yeah, that's fine, Rama. That's fine.
Yeah. So yes, if some person is asking, if you don't please forget about the yesterday attendance. No issue. From today onwards, we'll watching seriously on the attendance. Yeah.
Okay. Good.
Yes, sir. So
Then,
yeah, thank you so much.
Yeah,
We will see tomorrow the same time.
Yeah. Okay. Okay.
At 9:30 of UK.
Yeah.
Thank you so much.
Bye bye.